Today we're going to be tackling an interview question from Leetcode that Facebook loves to ask. Now, right off the bat, this video is going to be a little bit more difficult than my other videos thus far, but it's also the start of a cool series where I'm going to be tackling interview questions. The problem in question is to convert a binary search tree into a sorted, doubly linked list. And I thought the solution to this problem was really beautiful. That's why I wanted to talk about it. It's also worth mentioning right off the bat that a binary search tree can almost easily be converted into a sorted doubly linked list because an in-order traversal of the binary search tree, which is a fancy way of saying that if I scan a vertical line from left to right on the binary search tree, will produce a sorted encountering of items. So here I have an animation of what our input would look like and what our expected result is. Now, for those that are either new to CS, still learning, or that want to follow along to the best of their ability, let me quickly explain what we're dealing with here. So a binary search tree, or a tree in general, and a linked list, or a doubly linked list, are these sort of collections of these things called nodes. And what a node is pretty much represented by this circle with a number in it and with these pointers to other nodes. Node probably sounds like a fancy word to those that don't have experience with it, but that's as far as the definition goes. It's pretty much just some entity that has a value and that knows about other entities. Now, to sort of define the rules of the game, when we have a node, or when we're given a node, we can only access immediately the nodes that are next to it. Also, to kind of make those who aren't familiar feel better, we don't have to worry about how these things are coded yet. Algorithms are actually agnostic of programming, and we can pretend that we're trying to define instructions for ourselves to solve this problem generally on paper. So now that the refresher is done, let's get back to the actual problem. On the right of my screen, you can see that we have a doubly linked list. However, I still kept the nodes in the 2D positions that they were in when they were trees. Now, I'm just, for the sake of simplicity, going to flatten them into something that actually looks like a linked list. So either form that I'm representing here would suffice as a proper answer. Now let's get into the solution. As I said before, the input is going to be a binary search tree. And in general, we're going to represent our trees with one node that branches out to two subtrees, which all are composed of nodes if we were to zoom into them. Now let's define our solution and function in terms of visuals, right? So what I'm going to do is I'm going to say that this triangle with a square around it means that I'm doing a function call on a subtree. So the square represents the function call and the triangle represents the subtree that I'm solving the problem for. So if you were to see this square around the entire tree, that means we're solving the problem for the entire tree, which is exactly what we're doing. And as with all recursive solutions, what we're going to do is at some point solve the problem on the subtree, as you can see here. And now we get into why this solution is so beautiful. With recursion, as I've mentioned in my first video about recursion, once we call the function that's recursive on the subproblem, for example, this left subtree, we can assume that we solve the problem by the time we step out of that function call, which is crazy because that means that we can assume that if we square this triangle, the result is going to be the doubly linked list of that subtree, which is kind of overpowered or like almost unfairly easy, or perhaps suspiciously easy is a better phrase. So we did one of the core tenets of recursion right now. We assume that calling the recursive function on the subproblem will yield us the answer to the subproblem. In other words, now we can assume that we have the doubly linked list that represents the left subtree at our disposal. And now, naturally, the question is, what do we do next? Well, how about we do the same for the right subtree? We call the recursive function on the right subtree and now assume that we result with two doubly linked lists as well as the root of the subtree that we're working with. So again, we're left with the left doubly linked list, which represents, for example, items 1 through 10. Then we have the root of our subtree, which could be, say, 11. Then we have the right doubly linked list, which is now probably 12 through 20, say. Now we have three structures that we can use to form the answer to our current sub-problem. So I'm going to let you guys decide for a second how to proceed given these three structures to get the final answer for this outer subtree that we've been dealing with. All right, so the answer is that we simply take the end of the left list, tie it together with the root of the subtree we're dealing with, and then we take the start of the right list and tie it together with a root, and now we have the root integrated into these two doubly linked lists, making a larger doubly linked list that encompasses every element in every subtree. So at this point, we're pretty much almost fully done, but there is one more step left in our algorithm. And that step is to return the leftmost item in this resulting doubly linked list and the rightmost item in this resulting doubly linked list. And that specific step is how we can assume that we have access to the doubly linked lists of the subproblems. Let's say, for example, this current tree that we're looking at happens to be a subproblem in a bigger tree. Then if we return the head and tail of this subproblem, the bigger tree has access to the head and tail and can work with it as it needs to. And that will allow it to finish its recursive steps, and so on and so forth till we get to the top of the tree. Hopefully, this last demonstration gives you an intuition as to how we can possibly get an answer from just assuming that a subtree will be converted to a doubly linked list. It's almost magical that trusting and having faith in the fact that returning the head and tail of each subtree will allow you to generate a bigger linked list at each step. Okay, so now for the sake of a completeness of the algorithm, so that I can show you guys the code behind the algorithm, we have to consider an edge case. And there's two edge cases and they're mirrored. The edge case is that we're given a subtree that only has one child, either left or right. In the case that this happens, well, we simply just don't do a recursive call on the missing child, and we do a recursive call on the child that's there, and we see that that actually ends up working the same way if we use the root as the new head of the overall linked list. I'd also like to mention that the base case of this algorithm is that we run into a leaf that has no children, which is its own single node linked list. Okay, now the fun part, the code. I said I found this problem on Leetcode, so we're going to run our solution there. So in my solution, I have a function called helper, and that takes in the root, or the red square that I drew earlier, that represents the red square. So the most important case in our function is the else, which is where we have two children and we recurse on each. So immediately in that case, what I do is immediately recurse on the left subtree and then get the ends of the linked list that results from that recursion. And I do the same thing for the right subtree. And then I have every node that I need to rearrange to form the linked list that represents the current subproblem's linked list, the overall linked list. Notice the other cases that I've also talked about in which we only have one child, or the base case in which we have no children. So if I call this function on the root of the tree, then I should expect the entire tree to be converted to a doubly linked list, and I would also return the bottom left node of the tree and the bottom right node of the tree. And it's interesting to note that this problem on Leetcode actually asks you to also tie the first and the last nodes together, but given how we've coded this, that's very easy because we have access to the first and last node immediately after the function call. So what we do is we tie those nodes together, and that is our solution. And if I run it, it's a pretty decent solution. Sometimes it's under the curve, sometimes it's over the curve, but overall it's correct and it looks beautiful. Thank you guys for watching. If you guys have any recommendations on any other problems I should tackle and record, let me know.